Welcome to the Burrawon Branch Model Railway. I like helixes because they make good use of limited space. In fact, you gain more than you lose. For example, if I had opted for a single-deck layout design in the space I have available, the best I could have achieved would have been Burrawon terminus along one wall, with a short run of line into a fiddle yard on the opposite wall. By using a helix to a second deck, I was able to extend the operational and scenic opportunities on the layout by including the quarry, farm and junction dioramas. Helixes are an efficient means of getting trains between levels in a small space, and they hide steep gradients from view. People often ask me how trains run so reliably on the Burrawon Helix. When I ask them why they would expect otherwise, they have often had bad experiences with helixes or have seen poorly performing helixes. It seems that people build helixes without actively addressing certain elements that ensure reliable running. I built my first helix over 20 years ago to convert an existing layout from single to double deck. I have built another 4 since then. All have run very reliably. I believe this is because I took time and care getting everything in order during construction. This video considers the issues that I think are key to reliable running regardless of the helix design used. I have used the same basic design for 5 helixes on 3 layouts because it is relatively straightforward and reliable. That design uses 8mm threaded rods to raise the roadbed. The rods take up little horizontal space, so the track radius could be maximized. Also, the rods enable very accurate alignment of gradient and cant. I begin with the helixes as they set the location and elevation of all other framework and track work. I use 8-point star frames to which short lengths of timber are attached to support the threaded rods. For the roadbed, I use 2 thicknesses of 6mm external grade ply, overlapped by half a length. The overlapping lengths are glued together, resulting in a strong, stable, continuous roadbed that requires no other support than the rods. Easing the gradient onto and off the helix is important to reliable trouble-free running. Here, the gradient increases over a distance of about 2 meters from level to 1 in 55 at the helix entry. Accurate alignment of the transition curve onto the helix is also key to reliable running. The branch line gradient reduces to level between leaving the helix and the Burrawon yard entry. Let's take a ride up the helix while I outline what I believe are key to successful helix construction, regardless of the chosen design. A well-built helix repays the time and care taken during construction with reliable, trouble-free running across the life of the layout, so I work to get it right the first time. It's difficult to adjust or correct errors later. I plan every aspect before beginning. A stable track bed that doesn't twist or warp is essential. I accurately set the helix gradient and check it regularly with a level during construction. I don't rely on measurement alone. I ease the gradient onto and off the helix along a length of plane track, ideally 300mm or more. Canting the track bed 2 to 3 degrees from horizontal improves running and reduces the risk of derailments. I pay a special attention to track laying and use a trammel to ensure consistency of radius. I use the largest radius possible. The greater the helix radius, the lower the risk that buffers or couplings will lock and cause derailments. I ensure that track joints are seamless with no kinks or doglegs by using extra track pins either side of the join. I don't rely on adhesives. The track is tested as it's laid. I use a locomotive to push and pull the longest, the lightest, and the shortest wagons up slope and down. I use 3 or 4 wagons first, then full-length trains. I do it at different speeds too. This is also the time to check clearances for long stock, as well as looking for buffer locking and to ensure that couplings still have some sideways play. One further consideration is electrical connectivity. As the temperature range in my layout room is about 50 degrees centigrade, the track expands and contracts quite a bit. Therefore, to avoid track buckling, I don't solder the rail joints. Instead, I solder short lengths of wire between successive lengths of track. Additionally, I use booster cables from the main feed to ensure good electrical continuity along the helix. derailments should not occur if roadbed and track are carefully laid. The few derailments I've encountered over the years have most often been due to dirty wheels, poorly gauged wheels, and light wagons ahead of heavier ones that effectively push the light wagon off the track. If one wagon derails regardless of its location in a train, check the wheel gauge, as that may be the cause of the problem. I check the gauge of all new wagons before putting them on the layout. Perhaps as many as 10% of new stock are out of gauge. I have found that dirty wheels, especially the thick muck that can build up over time, can cause derailments on helixes, particularly at exits. Another problem that can occur is axles not running freely in their bogies. This is commonly due to dirt and gunk building up on the bearing surfaces. Excessive speed will likely deliver the result it deserves, particularly at downhill exits. On long trains, wagon order might be important for avoiding derailments. For example, it would be best to place light wagons at or near the end of the train. Weighting light vehicles according to the NMI guidelines can also help. Sometimes, differences in the lengths of adjacent wagons can lead to derailments on long trains. The helix track radius influences running in 3 ways. In general, running qualities should improve with increasing track radius. I have already mentioned that the potential for buffer and coupler locking is reduced with larger track radius. Additionally, larger track radius enables lower gradients to be used, which in turn means longer trains can be hauled up the helix. Finally, the actual grade is not the only limiter on loco pulling power and train length. The friction created by the constant curvature within the helix further reduces the effective pulling power of locomotives. The great John Allen is credited with devising a formula for calculating the impact that track curvature on hauling power. The formula generates the impact as a grade equivalent, which is added to the actual grade. The resultant effective total grade can be eye-watering. Let's look at how this affects Burrawon's effective gradient. The formula is quite simple. The answer is generated by dividing 32 by the track radius in inches. If using metric measurements, it is necessary to first convert those to inches by dividing the radius in millimeters by 25.4. First, let's convert the grade of 1 in 55 to a percentage, by dividing 1 by 55 and multiplying that by 100. So, the grade of the helix is 1.82%. That's a relatively moderate grade for a model railway. Generally, grades above 2.5% are considered steep. Now let's use John Allen's formula to calculate the effect of a 730 mm radius curve as though it was an incline. First, we convert 730 mm to inches by dividing 730 by 25.4. That's 28.74 inches. Then, we divide 32 by 28.74 to get an answer of 1.11. The convention when calculating grades is to refer to this as 1.11%. Now we add the helix grade and the impact of curvature to see that the effective grade is 2.93%. That's generally considered a steep grade. However, it's not such a problem on my layout, as the longest trains I run are 10 wagons, which are easily handled by a single loco. An effective grade of 3% would however have a significant effect on train length on a modern image layout.